Good morning all. Now I am going to explain about electrical machines. In this machines, first topic is transformers. Okay. First question: two windings of a transformer are designated as option A primary and secondary, option B primary and HV winding, option C secondary and LV winding, or are primary and LV winding. Option D HV and LV winding. Okay. In case of transformer, the windings are HV winding and LV winding, high voltage winding, low voltage winding. That is also decided based upon the number of turns. That means fourth option is correct. Next, two transformers A and B having identical ratings, are to be designed with flux densities of 1.2 Tesla and 1.4 Tesla respectively. Okay, the weight of transformer A per kVA would be, okay, now see here, transformer is a constant flux device. Okay, that is flux phi m is equals to, already we know that, maximum flux density B maximum into area of cross section AN. Okay, now see here, when B maximum, first case here B maximum is given as 1.2 Tesla, next case B maximum is increases to 1.4 Tesla. That means when B maximum is increases, we need to reduce area of cross section to maintain flux as constant. That means when B maximum is increases, area of cross section is reduces. When area of cross section is reduces, size is also reduces, hence cost is also reduces, hence weight is also reduces. That means transformer A weight is more than that of transformer B for same rating. That means from the given options, second option more than that of transformer B. That is, second answer is correct. Next, in power transformer, core is made up of with, okay, silicon steel. Okay, suppose in the option CRGO steel is there, then you have to prefer CRGO steel. Why? Because silicon steel is having a maximum flux density of around 1 to 1.2 Tesla, whereas CRGO steel is having approximately near value of 1.6 Tesla. That means here, in case of CRGO steel, B maximum is high, then cost and weight of transformers will be very less. Okay, that means third question answer is B is correct. Next, consider the following statements. First one is air core transformer are used in gate triggering circuit of thyristor. That is not correct. Next, second one, cores made of soft ferrites are used in pulse transformers. That means second option is correct. Next, third option is air core transformers are used in radio devices. This is also correct. That means second option is correct, third option is correct. Next, cores powered alloy are used in isolation transformer. That is not correct, right? That means 2 and 3 are correct. That means fourth question answer is B. Next, for a given cross sectional area of transformer core, stepped core are used. Okay, because of this stepped core, because of these steps, okay, the material required will be less. That means the conducting material required is less. When the conducting material required is less, means indirectly losses also reduces, right? That means it reduces conducting material and therefore I square R losses are reduces. That means third option is correct. Next, sixth question. A single phase core type transformer, LV and HV windings are arranged as under. Okay, always in case of core type transformer, first LV winding is placed, after that HV winding is placed. That means LV winding is placed near the core. Okay, after that HV winding is placed. But to reduce the leakage flux, half of the LV winding is placed near the core, after that half of the HV winding is placed, after that again half of LV, half of HV. That means from fourth option, half of LV near the core and half HV outside the LV of each limb. Okay, that means sixth question answer will be D. Now see here, see the solution for this one. For sixth question, see here, assume this is core. Okay, I am considering one side of core, right? First we need to place LV winding, after that LV insulation, after that HV winding, HV insulation. Then the cost of insulation will be less when we place LV winding is near the core. But to reduce the leakage, total winding will be, primary side winding is divided into LV winding is divided into LV by 2 into LV by 2 and LV by 2. That means half of the LV winding is placed on primary winding, half of the LV winding is placed on secondary winding. Okay. Next, a 400 by 200 volts, 50 Hz transformer operates at a flux density of 1.2 Tesla when energized from its HV. That means it is energized from HV side. From 400 by 200 volts, HV is high voltage is nothing but 400 volts, right? That means when E1 is equals to 400 volts and frequency F1 is equals to 50 Hz, its maximum flux density is 1.2 Tesla. Next, see here. For this transformer, linear dimensions of core are doubled while the number of turns are halved on both its HV and LV sides. Okay, in this transformer is now connected to 800 volts, 50 Hz. That means the transformer is again reconnected to 800 volts, 50 Hz. In this case, the linear dimensions are doubled. Okay, linear dimensions are doubled and linear dimensions are doubled and number of turns are halved. Okay, but already we know that EMF, already we know the EMF equation of a transformer, right? Okay, what is the EMF equation of a transformer? Already we know that EMF equation of a transformer is E1 is equals to 4.44 F into N1 into Bm into An, right? First case, what is given? E1 is equals to 400 volts, operated frequency is 50 Hz. At that point, maximum flux density is 1.2 Tesla. Okay, next, that induced EMF is changes to 800 volts, 50 Hz. What is the maximum flux density? Okay, when linear dimensions are doubled. Okay, when linear dimensions are nothing but length and breadth. Okay. Now see here, from this EMF equation, E1 is equals to 4.44 F into N1 into Bm into An, right? From this equation, Bm value can be written as E1 by 4.44 F into N1 into An, right? Now see here, from this equation, maximum flux density is directly proportional to induced EMF and inversely proportional to frequency and number of turns and net cross-sectional area. That means from that equation, I can write a formula as Bm2 is nothing but change, second magnetic flux density, Bm2 by Bm1 is equals to secondary induced EMF divided by primary induced EMF. Why? Because direct relation. Into inverse relation means opposite, right? That is F1 by F2. Starting case frequency is same, that means F1 is equals to 50, F2 is equals to 50. Next, N1 by N2, inverse relation, right? N1 is equals to N1 only, N2 is equals to N1 by 2. Why? Because number of turns are halved, right? In the problem only is mentioned, that is N2 is equals to N by 2. Next, what is given? Linear dimensions are doubled. Like that, length into breadth, that is new cross-sectional area is equals to length will be doubled, that is 2L, breadth will be doubled, that is 2 into B. That means 4 into length into breadth. Already we know that length into breadth is nothing but AN1. That means AN2 is equals to 4 times of AN1. Okay, substitute all those values, that is BM2 is equals to BM1 into E2 value is 800 divided by 400 into frequency F1 and 50, F2 is 50, right? N2 is N1 by 2, then 2 comes to numerator, that is 2 into N1 by N1, N1 and N1 will be cancelled, into AN1 by AN2 value will be 4 into AN1, AN1 and AN1 will be cancelled. Numerator side 800 into 2, 1600, denominator also 400 into 4, 1600. Right? That means 1600 and 1600 will be cancelled, that is Bm2 is equals to Bm1. That means maximum flux density of second transformer is also same value only. That means what is the same value here? Here what is the problem? First case 1.2 is given, right? That means this answer is also 1.2 Tesla only. Seventh question answer is B is correct. Next, eighth question. For core type power transformer, both primary and secondary windings have circular coil section because this section has strongest mechanical shape. Okay, that means what is the answer? Eighth one will be C is the answer. Next, transformer action requires a alternating magnetic flux, but the flux in the transformer core is maximum flux, that is used in EMF equation of a transformer. But in this given option, third option is correct, C. Next, in a single phase transformer with subscripts 1 and 2 for the primary and secondary winding. Okay, already we know that in case of transformer, E1 by E2 is equals to N1 by N2. That means E1 N2 is equals to E2 N1. Okay, similarly I1 by I2 is equals to N2 by N1. Okay, that is I1 N1 is equals to I2 N2. That means all these results are we are getting from transformation ratio K. K is equals to N2 by N1, that is equals to E2 by E1, that is equals to I1 by I2. Okay, from that result first option is correct. 10th question. Next, the flux involved in the EMF equation of a transformer. Okay, EMF equation of a transformer is E1 is equals to 4.44 F into N1 into phi m. Okay, phi m is nothing but maximum flux, right? That means 11th question answer will be D is correct. Next, for understanding the behavior of a transformer, the following laws may be called for. Okay, first one, Lenz law. Lenz law is used in case of transformer. Okay, opposite sign, opposite sign, negative sign represents Lenz law, right? Induced EMF formula, E is equals to minus N into d phi by dt. That means first point is correct. Next, Newton's second law. Here we didn't use Newton's second law, right? That means that is not correct. Next, third option, Faraday's law of electromagnetic induction. That is correct. That means 1 and 3 are correct. Next, Ohm's law. Okay, we can use Ohm's law also here. Fourth one is also correct. Next, Fleming's right hand rule. That is used in dynamically induced EMF. In statically induced EMF, we can use right hand grip rule. That means 1, 3, 4, 6. That means 12th question answer is fourth option, D is correct. Next, in an ideal transformer, if K is some constant, then the supply voltage is V. In terms of its magnetizing current, Im can be expressed as, okay, that is J into K into F into Im. That means first option is correct. Okay, thank you all. Remaining we will see in next class.